Alright, welcome to another Calculus 2 integration method video. Today we'll be talking about trig substitution, which tends to not be students' favorite just because it tends to be taught, I think, in a harder way than it has to be, as well as it just being a little bit longer and hard to simplify at times. But it's not too bad once you kind of try a few and kind of are aware of the way it works. So the way they usually look like are usually some sort of like a fraction, and they have some square roots, or just usually one of them, and some x's. They'll have a look for them. The way you'll know, let's just say it's x cubed over x squared minus 9, let's just say dx, right? Something like this. The reason how this is a trig substitution problem is if you try to use u substitution, you won't be able to cancel out this x cubed. Usually they'll have this square root x look anyway, so you can kind of deduce that it's going to be that problem, but it won't work if you use substitution anyway. So how it works, the first thing I think is very useful to do is we're going to apply the triangle method. Okay, so we're going to draw a triangle here. It's going to be a right triangle, and this is where the theta, the angle, is going to be in this corner, this side, angle right here. So what we're going to be doing is we're going to be looking at this square root, and we're going to be deducing it from there. So let's write this square root just so I can show you the process. So if you notice, we're going to be utilizing the identity a squared plus b squared equals to c squared. The reason we're going to be doing this is if you look at the square root, the first step is you look at the square root and there's a plus, then you know that what we did with the identity is we square rooted this and we square rooted this. So then c equals to both of these being added. But if you see the minus, what it means is that we've subtracted one of the sides, so one of the a or the b, and we have that a squared equals to c squared minus b squared. And then we take the root of them both, and we have that, a is equal, or a squared, a is equal to the hypotenuse minus one of the sides. The reason it's important to look at this visual is just you can decide how to make this triangle, and therefore kind of substitute things in. Now I know this seems really random and this seems like it might take a longer time to do, but trust me when I say that doing it this way is much better than trying to sub in with memorize things. It just makes it much easier to solve. So let's do that then. We have a minus here, which means we're dealing with the option 2. That means the c squared minus b squared with the root with the minus means that this first one is the hypotenuse. Okay, so this one here is the hypotenuse. We're going to put it right here on the hypotenuse side. Okay. Now the other two sides, the trick with it is, now it works either way, but it's much quicker to simplify if you just remember this idea that whenever you have to choose between the two sides, the more complicated side, so the one with an x in it, whatever one with an x in it, is the side you want to be on the vertical leg here. So that means that the 9 here is going to be one of the sides, okay? So, but remember that when we're taking and we're putting on the side, we're taking the square of all of these because it's in a square root, which makes sense. So x squared, we put x because the square root of x squared is x. Now the square root of 9 is 3. So we're going to put that on the less complicated side, this bottom one. So we're putting a 3. Now whenever you have the first two, the last side is always going to be the root function, so just the root as a whole. So the root in this case will go on this side, x squared minus 9. After you've made your triangle, what you're going to be doing is you're going to set up a angle, like a trig angle relationship to them, so we can sub them for trig angles and solve this. Okay, so the way that works is first we have to find x. Now if you notice, x is going to be this hypotenuse, and we want to always incorporate the number into the relationship because the number will allow us to isolate the variable easily and solve it. So for example, the hypotenuse here is x, and to the angle theta here, it's the adjacent side. The 3 is the adjacent side. So we know that adjacent over hypotenuse is going to be cosine. Now just remember, we always want the x, or the variable one, to be on the first side. So what that means is we're going to have x over 3, which would be hypotenuse over adjacent. And that's the opposite of cosine, which is the secant. So secant of theta is equal to the hypotenuse, x, over the adjacent, 3. And what we want to do is we want to solve for the x. So if we cross multiply, then it's 3 secant theta equals to x, because x times 1 is 1, x. So we'll have 3 secant theta equals to x. And then following that, the next thing you want to solve for is the dx. So we've solved for x, now we want to solve for dx, so we can simplify, sub it in later. So the dx, okay, is going to be the derivative of x. So the derivative of secant is secant theta tangent theta. The 3 remains, so it's secant theta tangent theta. Okay, this would be just solving for the dx from the x. Then we want to solve for the root function, because we see the root function in the equation, so we want to solve for the root function. Now the root function, in relation to the angle here and the number, so the standard number, 3, would be, if we want to put it on top, right, and we know this is the opposite side to the angle, and this is the adjacent side, which is tangent. So we would say that tangent of theta is equal to the opposite side, the root x squared minus 9, over the adjacent side, which is 3. And then if we cross multiply just like before, right, then it's 3 tangent of theta equals to the root of x squared minus 9. And finally, we know there's x cubed in our actual integral, so we need to find x cubed. Luckily, that's pretty easy to do. We already know what x is, so if we cube x, we have to cube this. So 3 cubed would be 27, right? Because 3 squared is 9, and then 9 times 3 again is 27. So 27. And then secant cubed would be secant cubed of theta. Okay? So I know this seems like a ton of extra work for this one, just make all of these arbitrary things, but I promise you when I say it's going to make this whole process miles easier to complete than I think the standard practices. So we're going to just put in everything that we found. So x cubed we have is 27 secant cubed. So 27 secant cubed of theta is for x cubed. Our root is equal, or the root of x squared minus 9 is equal to 3 tangent of theta. So here's 3 tangent of theta. And our last thing to sub in is the dx, and the dx is 3 secant theta tangent theta. So again, all we're doing is we are just simplifying. We're just subbing in each of these to their trig angle. Okay, the next thing I advise you doing is putting any constants out. It's just going to make it much easier to simplify. So 27 divided by 3 is 9, right? If we think of this like 27 divided by 3, that's 9. And then 9 times 3 gives you 27. So again, this is 27 by 3, and then 9 times the 3 here in front of that was the, oh, I apologize too. This should be a d theta, so don't do what I did. Don't forget your d theta, otherwise it's not an integral. But anyway, you have the 9, and the 9 times 3 is the 27. So we're just going to move the 27 out front. So we just simplified all the constants, which we're allowed to do, and we just move the simplified constant out front, okay? And then we're going to rewrite all of the trig functions as they were. Okay? All right. So now it's secant theta, tangent theta, d theta. Okay? Now what we're going to be doing is we're going to see if there's anything that could cancel or come together. And it looks like there is, right? This tangent here can be canceled with this tangent, just like in u substitution. And this secant can multiply with this pre-existing secant to give you secant to the 4th, because we're just going to add the exponents. So 27 times secant to the 4th theta d theta. Now you're going to find there are multiple ways to simplify these sometimes. You don't have to do it just one way. Like whatever way you can see right away, that's the way you'll use to simplify it. That can be frustrating at times, which is why it's just something you want to practice doing. But the way usually what will work is either changing the functions into a different form, combining them together, and then maybe using like a trig integral, so another integration method. Trig integrals seems to be a good call here because we can do a few things. So first, we can break up the secant to the fourth into secant squared 2 times. And then if you notice, secant squared theta could be some sort of derivative. So let's maybe see if we can do that. Let's say we want the du to be the secant squared theta, and then the u to be what derivative, what function we give a derivative for secant squared. And that's probably going to be tangent of theta. Tangent's derivative is secant squared. So let's see if we can manipulate the function to work in terms of tangent. It may not, like if it doesn't, that's okay. You just kind of have to try again. This is why these tend to be a little more annoying for students. But that's just kind of part of the process. So we need secants to be in tangents. Luckily, we know an identity, and luckily this is a square, so we can utilize it. So the identity is 1 plus tangent squared of theta equals to secant squared of theta. We need it to be in tangents, so let's just replace secant squared with 1 plus tangent squared, which would be 27, and then we would sub this into 1 tangent squared of theta, and then we'd have secant squared of theta d theta. Like I said, we know this would be d theta. We know that we need to be in tangents, which they are, and we have a du secant squared. And if we divide it by secant squared, we would get that d theta is equal to secant squared theta. Sorry, it should be du over secant squared theta. So this should be that the d theta is equal to du over secant squared theta, just like normal u substitution. Okay, so then we're going to have 27. And now that we have everything here in terms of tangents, we can very easily say it's 1 plus u squared, since our u was tangent, we decided it could be. And then secant squared theta will remain, and our d theta was equal to du over secant squared theta. So du over secant squared theta. We're just subbing this in. So the secant squareds can cancel. Now we have 27 times integral of 1 plus u squared du. And finally, this is a pretty easy polynomial now. We started with this, and now we're here. So we're just going to simplify it out. This is going to be 27 times, this whole thing needs to be distributed eventually, but 1 integral of 1 just turns into u, and then it's going to be this one, the power rule is u cubed over 3, and then of course the plus the c. I'm just going to move up here to finish the problem. Let's just clear this up though. So then if we have this, we're just going to kind of distribute the 27 in. So that turns into 27 a u plus 27 u cubed over 3 plus c. We're just going to do a little bit of simplification here, right? Because 27u stays, but 27 divided by 3 is 9, so that's 9u cubed plus c. We know u is going to be tangent of theta, so that's 27 tangent of theta plus 9 tangent cubed of theta plus c. And it's tempting to say we're done, but the next thing we have to do is we need our answer in terms of x. We started with dx, so we can't have theta as our answer, which means we just have to know what was theta, like in terms of what was tangent theta equal to. And luckily, we know that tangent theta is equal, so not this one, right? This is isolating tangent with this one, but we want to know tangent theta is equal to this, the root over 3, what we calculated all the way over here. So we're just going to put that in. That's going to be 27 times the root of x squared minus 9 over 3 plus 9 times the root of x squared minus 9 over 3 plus c. And finally what we can do is, since we've just put in, we have tangent of theta, right? And we knew what tangent of theta equals to in terms of x. We found that all the way up here. We subbed that back in. That's all we did. We kept it all the same. Oh, and I apologize. This should be a cubed. Don't forget that. And actually, be right back. I'm just going to clear a little bit of space, and then we'll kind of continue doing. So I'm just going to clear up a little space, and now we're going to put this in. So we can put the 27 here. Is 27 times the root of x squared minus 9 over 3. This is perfectly fine. We're going to cube this. So if we have this, like, this root is to the 1/2 power. So 1/2 plus times the 3, that's like 1/2, right, times 3 over 1. Since they're multiplying, since it's an exponent to an exponent, that gives you 3 over 2. So this is the same thing as saying 9, right, times this whole thing, x squared minus 9 to the 3 over 2. If we just cube the 1/2 power, like we just said, then this one would be cubed as well, right? So cubed, we cube this, we also cube this. So 3 cubed is, of course, 27, and plus c, okay? Finally, though, we're not quite done. 27 divided by 3 we know is 9. So this is 9 times x squared minus 9, the square root, and then 9 over 27, that's of course going to be 1/3. That's the same thing as saying 1/3. So there's a 1 here, but we're just not going to write it. So it's going to be x squared minus 9 to 3 over 2. And then 9 over 27, that's 1 over 3. So we're going to put 1 over 3 on the bottom. And then plus c. So the whole answer to this function is going to be this right here. So as you can see, it's kind of a lengthy process. It takes a while, but trust me when I say, if you look up other methods, some of them like to give you some general things to memorize in terms of the angles, and then you have to make the triangle again at the end, which adds more time. So it actually, I think, ends up taking more time to work it out another way as opposed to this. This actually cuts away some time. Okay, we're back for another one. This one is going to seem kind of innocent in terms of a function. There's actually no way to do this other than trig substitution, because we can't use sub this because we'll be left with an x. So it doesn't actually work. So we have to use substitution here. So like I said, the thing to do when you recognize that trig substitution probably is a good bet is we're going to be making the triangle here. And the reason why we don't want to use trig substitution right away is because, as you saw with the last example, it's pretty long. It's pretty long to do it. So it's much easier to use any other method literally than it, if you can. And since we can't, we kind of have to. Our hands are tied. So we're going to do the same thing, okay? So we're going to look at this root. Okay, just look at this root. So as we can see, we have a minus here. So we know that our hypotenuse, right, is going to be the thing, the c squared here, because the leg has been minused over. So our c squared, or hypotenuse, will be this 1. Of course, the square root of 1 is just 1, so it's going to look like that. Our other leg is x squared, so we take the square root of that, that's x. We're going to put this x, though, on this side here, because the more complicated leg is the full root 1 minus x squared, and we're going to put that on the vertical leg. Like I said, it's okay if you don't do that. You sometimes will have to work with cotangents and cosecants if you don't put the more complicated one on the vertical. I mean, it works just the same, but usually people don't have cosecants and cotangents as clearly memorized in terms of the negatives and stuff. But it works. So in terms of this, though, that's what I recommend. Now we're going to try to find this. So we really just have to find x first. So x would be this side, the adjacent, right? And we want to incorporate the 1. So adjacent over hypotenuse, well, that's cosine. So the cosine of theta is the adjacent x over 1. Now because it's just 1, it's just that equals to the cosine of theta equals just to x. And then we want to find dx, just like last time. So dx is going to be the derivative cosine, which is of course going to be negative sine of theta, and then this is the d theta. And then our root function, which is what we need as well. So the root function is going to be the opposite to this angle here over hypotenuse, which is of course sine. So the sine of theta is the opposite, the 1 minus x squared over the 1. So the sine of theta is just equal to 1 minus x squared, just because it is a 1. This kind of simplifies nicely in this example. Then what we're going to do is we're just going to put these things in that we need. Okay, so we know that the in terms of this one right here, the root of 1 minus x squared is equal to sine of theta. So we're just going to put sine of theta in, and then our dx is equal to negative sine of theta negative sine theta d theta. So negative sine of theta d theta. Well, we have a negative, so we're just going to move that outside. We don't need to deal with that. And sine of theta times sine of theta is, of course, sine squared of theta. And this actually looks like kind of a nice integral to solve. Unfortunately, this kind of is a little bit of a problematic one. We have to use double angle identities because sine squared by itself can't be u subbed either. So we need to know the identity. We need to know is that sine squared of theta is equal to 1/2 times 1 minus the cosine of 2x. So we're just going to input that in exactly how I wrote it. So 1 minus the cosine of 2x d theta. We can take out this 1/2 because it's just a constant. And we're going to have 1 minus the cosine of 2x d theta. Now I, in a previous example, showed you u substitution for the cosine of 2x. It's just a standard u sub problem. The trick for these, though, is you can take a linear term and understand that it's just going to be the reciprocal of this the whole number here. So it's going to be 1/2 in front. If you want to know the substitution, look at my trig integral video. I have that kind of quick process laid out for you. But in terms of that, we're going to have 1/2 times the integral of all of these, so subtracted. So the integral of 1 is, of course, just going to be x. Oh, you know what? I am very sorry. These all should be theta. We're not in terms of x. So don't switch your variables by accident. We need to be in terms of x. So integral of 1 is just theta. And the integral of cosine is sine. So we're going to have sine of 2 theta. And then it's a linear term, so we can take the reciprocal of it, which is 1/2. And then it's going to be plus c. Now this trick only works with linear terms though, but you're free to use it for any function like this minus that has the linear term in it. Now we're going to distribute the 1/2, so this turns into negative 1/2 theta minus 1/4 sine of 2 theta plus c. Now we're going to do our trick we've been doing. So we know what we don't, unfortunately, know what theta is or 2 theta. So we don't know what any of these are. We know what sine of theta is. We don't know what sine of 2 theta is. So we actually have to use 2 tricks on both of these. The first one's going to be easier than the other one. The one to input first, though, is we want to get rid of this 2 theta since we don't know anything 2 theta. Now, another identity we just kind of have to know from trig is that the sine of 2 theta is equal to 2 sine of theta cosine of theta. That's just an identity to know. And so we're going to have 1/2 theta minus 1/4 times 2 over 1 if you like, times the sine of theta cosine of theta plus c. We have this one will stay the same, and we can multiply this. 2 over 4 turns into 1/2 times the sine of theta cosine of theta plus c. Now we can, we're going to move up here just so we have more room. We have to input a little bit of a trick here because we know what sine of theta actually is. We know what cosine of theta is now. We've gotten rid of that issue. We still have the theta issue. Now to solve for theta, we're just going to isolate theta really quickly in this example. So cosine of theta is equal to x. So if we take the arc cosine, inverse cosine, the arc cosine, right, we'll cancel out the cosine. So if we said the cosine of theta is equal to x, as we solved, then if we take the arc cosine, then these will cancel. And if we take the arc cosine on this side, then we have that theta is equal to the arc cosine of x, right? And that makes sense. That's perfectly true. So now we know what theta is equal to just by using a quick little simplification. That's going to be negative 1/2. We know theta now is arc cosine of x. So what we're doing is we're trying to replace theta with x to finish the problem. So that's going to be the arc cosine of x minus 1/2. We know that the sine of theta in this example is the root of 1 minus x. So the root of 1 minus x squared. And the cosine of theta is going to be x. Ahead and kind of work out any last simplification. So the 1/2 arc cosine of x, that's fine. Now the 1/2 can just kind of stay in front of this if you'd like. It's going to be 1/2 times x root of 1 minus x squared. This should be a plus c and a plus c. So this is kind of what your answer would be. So like I said, it starts off kind of simple, but just kind of showing you that in terms of breaking it all down, it takes a little bit of tricks and simplification. And yeah, that's how it works.